In analyzing acid-base disorders, I use the bicarbonate-centered approach, and this is also called the Schwarz-Barter approach. The universal laws of nature must be obeyed, even in acid-base disorders. This includes the law of conservation of mass, in which matter cannot be created or destroyed, the first law of thermodynamics, in which energy cannot be created or destroyed. An organism in a closed system is therefore always in a state of energy equilibrium. All modern theories of acid-base balance are predicted upon the thermodynamic equilibrium equations. We use the anion gap to study acid-base disorders, and this is best represented using the Gamblegram developed by James Gamble in the 1950s. And in this, he emphasized the importance of charge balance. The anion gap is a reflection of unmeasured anions, and this is calculated by taking measured cations minus measured anions. Therefore, the formula will look like this: serum sodium minus the sum of chloride and bicarbonate. Potassium is omitted as the variability is low. A normal individual will therefore have an anion gap simply because the quantity of the cations that we measure is much more than the quantity of anions that we measure. The expected anion gap in a healthy individual depends on laboratory calibration, and this is usually taken as 12 milliequivalents per liter. This is the anion gap represented with a Gamblegram. It is most important to emphasize that the cations and the anions are balanced in electrical neutrality. This is the anion gap in which we take the total sodium minus the bicarbonate and the chloride. What is the normal anion gap? And for this, we have to go through the concept of the expected anion gap. Normal anion gap is assumed at 12 milliequivalents per liter. But the bulk of this serum anion gap that we see here, which is unmeasured, is usually due to the sum of the anionic charges of albumin. Albumin is very weakly negatively charged, but due to the high amounts in the plasma, it contributes a significant amount of the anionic charges. The expected anion gap can be illustrated using the Gamblegram. In a patient with normal amounts of albumin, this would be the expected anion gap, usually taken at 12 milliequivalents per liter. In a patient who is hypoalbuminemic, the expected anion gap would therefore be much lower. There are a few studies that try to explore the effects of low serum albumin on the serum anion gap. This study by Figge and Fenkel is the most often quoted. For every 1 gram per deciliter decrease in serum albumin, the serum anion gap would decrease by 2.5 milliequivalents per liter. If you use the units in grams per liter, for every 1 gram per liter decrement, the serum anion gap would decrease by 0.25 milliequivalents per liter. In high anion gap metabolic acidosis, we see a net gain in anions that are not measured. This could be due to lactate, ketones, uremia, or exogenous anions. This results in an increased anion gap, and in order to maintain charge neutrality, bicarbonate levels are suppressed and titrated away by the organic acids. The chloride does not change, and therefore high anion gap metabolic acidosis is sometimes called normal chloremic metabolic acidosis. The commonest causes of HAGMA would include lactic acidosis, ketoacidosis, which could be due to diabetic ketoacidosis, alcohol ketoacidosis, or starvation ketoacidosis. HAGMA could also be due to renal failure or the accumulation of uremic toxins and the retention of hydrogen ion. Finally, HAGMA could be due to the ingestion of exogenous substances. You could use various mnemonics to help you remember what are the endogenous and exogenous substances that may cause a HAGMA. Do a search in Wikipedia for get acidosis and you will find a few mnemonics listed in Wikipedia. Some factors may interfere with the interpretation of the anion gap. For example, in paraproteinemia and multiple myeloma, this may cause some deviation in the anion gap, depending on the subtype of the paraproteinemia. This is because IgG is cationic, while IgA is anionic. Other electrolytes with positive and negative charges may also interfere with the anion gap. The albumin charge will also vary with the pH of the blood. If the patient has a pH of 7.4, for every 1 gram per deciliter change or decrease in albumin, this would decrease the anion gap by 2.8 milliequivalents per liter, but the effect is less pronounced in acidemia with a pH of 7.0, for which 1 gram per deciliter of albumin will reduce the charge of anions by 2.3 milliequivalents per liter. Sometimes we identify a HAGMA, but we are unable to explain it in terms of the traditional causes of lactate, ketones, uremia, and exogenous substances. This could be due to the presence of other types of unmeasured anions, and the possible candidates are pyroglutamic acidemia. Pyroglutamic acid is produced by the enzyme gamma-glutamyl cyclotransferase. The gamma-glutamyl activity increases when the glutathione levels are low, and glutathione can be depleted with paracetamol, alcohol, severe sepsis, liver, and kidney diseases. Decreased activity of 5-oxoprolinase, which breaks down the pyroglutamic acid, may also play a role. The unmeasured anions could also be due to Krebs cycle intermediates or other mitochondrial intermediates. These are very difficult to measure as it degrades rapidly on standing. Finally, an unexplained HAGMA could be also due to D-lactate isomers. For example, this may occur in a patient with bacterial overgrowth and short gut syndrome.